Hi, and welcome back to my channel. Today I'm going to be doing a COMSOL tutorial on modeling vibration and noise in a gearbox. And unlike most of my tutorials, which only require the COMSOL multiphysics, this one requires additional products. So we'll be using the acoustics module, the CAD import module, and the multibody dynamics module. Alright, so let's go over the background information since this is pretty involved. The gearbox is used for transferring power from the engine to the wheels. Predicting the vibration and noise radiation from a dynamic system like a gearbox gives the designer an insight early in the design process. When operated, a gearbox can radiate noise in the surrounding because of two reasons. The first and foremost is the transmission of undesired lateral and axial forces on the bearings and housing while transmitting power from one shaft to another. The second reason is the flexibility in the different parts of the gearbox, such as the gear mesh, bearings, and housing. This example illustrates a model of vibration and noise in a 5-speed synchro mesh gearbox of a manual transmission vehicle. Transient multibody analysis is performed to compute the gearbox vibration for the specified engine speed and external load. The normal acceleration of the gearbox housing is converted to the frequency domain and used as a source of noise. An acoustics analysis is then performed in order to compute the sound pressure levels in the near, far, and exterior fields. So here's our geometry that's supplied as an MPH bin file. So thank goodness we don't have to create this from scratch. If you had a typically if this were real world, you would have a CAD file and you would just import the CAD file. Okay, so we've got a housing, a bearing, first gear, second gear, third gear, fifth gear. Where's the fourth gear? Why does it say fifth gear but there's no fourth gear? Main drive shaft, output in, counter shaft, fixed. Okay, so these are fixed components. The housing is fixed, and then this. So here's our 5-speed synchro mesh gearbox of a manual transmission vehicle. The geometry of a synchro mesh gearbox is shown in figure 1. Only those parts of the gearbox which are relevant from a physics point of view are considered for the analysis. Alright, so we have other parts, but they wouldn't be relevant. The gearbox has a varying gear mesh stiffness which causes vibrations. These vibrations are transmitted to the gearbox housing, and the housing further transmits energy to surrounding fluid, resulting in acoustic wave radiation. In order to numerically simulate this entire phenomenon, the following analyses are performed. Multibody analysis. The first step is to perform multibody analysis of a gearbox in order to compute the dynamics of gears and the housing vibrations. The multibody analysis is performed at the specified engine speed and output torque in the time domain. Acoustics analysis. As a next step, a spherical domain enclosing the gearbox housing is created in order to perform acoustics analysis and compute the sound pressure levels outside the gearbox. Part 1, multibody analysis. The gear arrangement in the synchro mesh gearbox is shown in figure 2. Alright, so here's the side view of the geometry, the internal geometry, the moving parts, the main drive shaft and the counter shaft, gears 1 through 5. The synchronizing rings used to connect the gears with the main shaft are not physically modeled here. The gearbox considered here has its main or drive shaft connected to the counter shaft using helical gears. The multibody analysis is performed in the time domain for one full revolution of the drive shaft. Gear mesh is assumed elastic. The number of teeth of all gears are given in figure 2. So a pressure angle is alpha, is 25 degrees. The helix angle is beta, which is 30 degrees. The gear mesh stiffness, K sub T, is 10 to the 8th in units of Newton per meter. So this is a, let's see, force per length Let's see, if it was force per area, that'd be a pressure. Force per length, that's like a pressure times length. Okay. All the gears on the countershift are fixed to the shaft, whereas the gears on the drive shaft can freely rotate. Only one gear at a time is fixed on the shaft. In real life, this is achieved with the help of synchronizing rings. In this model, the synchronizing rings are not physically modeled. Instead, constraints are used to engage the gears with the drive shaft. In order to engage fourth gear, the input end of the drive shaft gets directly connected to the output end of the drive shaft, bypassing the countershaft and making the unit gear ratio. Housing. Both the shafts are rested on the housing through hinge joints. The housing is assumed flexible and made of structural steel. It is mounted on the ground as well as connected to the engine at one of its ends. Note, to reduce the computation time, linear elements are used in the discretization while modeling the housing. To get more accurate results, quadratic elements. While the gearbox is in operation, it starts vibrating under the influence of various forces. The normal acceleration of the housing, a measure of the noise radiation, is shown in figure 5. Whoop. Down here, figure 5. So we've got the top color legend is for the velocity surface plot in meters per second, and the housing shows the surface plot for normal acceleration. It's the rainbow surface plot. The high acceleration has to correspond to the magnitude in the negative direction for the counter shaft. You have to rotate at the same time, accelerating at the same time. Same magnitude, opposite direction. In order to have a better understanding about the frequency and content, we can transform these results by using FFT solver as shown in figure 7. Okay, I guess it's saying, so we're gonna have component 1 is in the time domain, component 2 is going to be in the frequency domain, and then we have to use a non-local coupling called a general extrusion, which I've never used before, to map the values between the two components. Presence of a multibody dynamics physics interface by default forces the solver to be nonlinear. Hence, it is manually set to linear for the acoustic analysis. Interesting. And also, this is the application library path. Alright, so let's jump into the modeling. We're going to do a 3D model today from Model Wizard, and then we're going to expand structural mechanics by Multibody Dynamics. MBD. Add. And then we're going to select time dependent for study. And done. Alright, for the geometry, since this is a complex geometry, they supplied the file for us. So we're going to go from Home Toolbar to Import. First, let's save this. Alright, so from the Home Toolbar, click Import. And then we're going to go to Browse, the folder icon, and Gearbox Vibration Noise MPH bin. And this will be available at the link in the description of this video. Form Union. So in Component 1, Geometry, click Form Union. In the Settings window for Form Union Assembly, locate the Form Union section. Alright, from the action, we're going to change from Form a Union to Form an Assembly. Clear the Create Pairs checkbox and Build All. Alright, and here is our gearbox. Zoom extents. Click the Click and Hide button in the Graphics toolbar. So this icon with a line through an eye. In the Graphics window toolbar, click the down arrow next to Select Objects, then choose Select Domains. Here we go. So instead of Select Objects, we're going to select Domains. on the object fin, select domain 4 only. So our form assembly, we have to find domain 4. All right, there we go. Click on the click and hide button in the graphics toolbar. In the model builder window under global definitions, click parameters 1. In the settings window for parameters, locate parameter section. We're going to go to the load from file icon and select the text file that I saved previously, Gearbox vibration noise parameters.txt. Right, and there we go. We've got quite a few parameters here. We've got the number of teeth for the first gear through fifth gear, the gear ratios, the center distance, the pitch diameters, the helix angle, engine or main shaft speed, the time period of the main shaft rotation, output torque, gear mesh stiffness, the sphere radius, and engaged gear. So now we're ready for variable input. In the model builder window, expand the component 1 definitions node. So these are local variables we'll be defining. Right-click definitions and choose variables. In the settings window for variables, we're just going to put in this expression for a new variable an nbd.u underscore ttx times nx plus multibody dynamics.u underscore tty times ny plus nbd.u underscore ttz times nz. Normal acceleration. Okay, so now we need to create a step transition for smoothing. So we're going to go to Home Toolbar, click F of X for functions, and then choose Global Step. And in the parameter section, in the location, we're going to put T over 40. Click to expand the smoothing section, and in the size of the transition zone, we're going to put T over 20. And if we go back to parameters, we can go see what T is. It's the time period. T is the time period of the main shaft rotation. So 2 pi over omega, where omega is the engine or main shaft speed. Okay, so remember how last time we talked about scope of variables? So step isn't necessarily a variable, but we can still talk about scope because the step falls under global definitions. So that means the scope of the step is going to apply to any subnodes of the root node. Whereas if it were under component 1, it only applies to component 1. And then in the smoothing section, we put T over 20. Alright, so our parameters location is T over 40 from 0 to 1. So recall T is an inverse parameter, that's 2 times pi, T is an inverse speed, so 2 pi over omega, omega being the speed of the engine shaft to make one rotation. And so if T is over 40, so basically a 40th of the critical time element, the critical time dimension. That's the location of it, and it's occurring from 0 to 1, so it's a normalized smoothing or a normalized step function by definition goes from 0 to 1. And then our smoothing, the size of the transition zone is T over 20. So we've got T over 40 plus or minus T over 40. So that gives us a smoothing zone of t/20. And the number of continuous derivatives, our default is 2. All right. Okay, now we need to add explicit 1. In the definitions toolbar, click explicit. So this is in the third column, first icon. In the settings window for explicit, locate the input entity section, and then we're going to choose boundary from the geometric entity level. And from the geometric entity, let's click paste. All right, so here's another way to enter. We've talked about selecting just by hovering and finding which domain or boundary you want. In a complex geometry like this, it's giving us the option to just click on paste, and you can either paste the selection in there or type it. So we're going to type 367 to 370. Click OK. And now we need to add another explicit. Right-click explicit 1 and choose duplicate. And for our input entities, we're going to clear selection. So the little broom icon, and then click paste selection again, our clipboard icon, and we're going to type these ranges here, 372 to 375, comma, 377, 379 to 381. And if you want to see what those are, since it's kind of hard to see it with a geometry like this, what we can do is click the transparency icon here, and you can also use the wireframe rendering if that helps. And another way you can zoom in is this icon right next to zoom extents, zoom to selection. All right, explicit 3. We're going to right click explicit 2 and copy, or sorry, duplicate. And in the settings, locate the input entity section. So we're going to clear this selection, clear, paste. And we're going to type in 818 to 821. All right, so let's take a look at where that is. Zoom to selection. Let's do transparent and wireframe, and zoom extents. So this looks like the end of the counter shaft, the end point of the counter shaft. All right. Explicit 4. We're going to duplicate explicit 3, clear selection, paste, and then type in 824 to 826, 828, 830, 832 to 834. Okay. And that is the endpoint of the main drive shaft. You can see highlighted there. Again, we're going to duplicate explicit 4, explicit 5, clear selection, type in these ranges, 184 to 190, 193 to 209, 214 to 217, 226 to 240, 242 to 246, 533 to 540, 602 to 613, 677 to 680, 683 to 690, and that's it. All right, so all the purple regions, this looks like it's the bolts on the permanent or on the fixed components. All right, explicit 6, we're gonna duplicate once again, clear selection, and this time we're doing domains instead of boundaries. So we're gonna change the geometric entity level to domain, and then go to the paste section and enter domains 1 through 8. Okay, so it looks like the housing components. All right, and in the settings window for explicit, locate the output entities section. From the output entities list, choose adjacent boundaries. General extrusion 1. And the definitions toolbar, so I'm going to go up here to definitions, click the link icon for non-local couplings, and choose general extrusion. Alright, so we're adding a general extrusion non-coupling as it said in the background material because one of our components, the physical multibody dynamics, uses time frequency or time domain, and component 2, which will involve the sound or the acoustics, is going to be in a different domain, the frequency domain. So we need a non-local coupling to make that work. Okay, so we chose our general extrusion non-local coupling. And then the settings, we're going to go to source selection. From geometric entity, choose boundary. From the selection list, choose explicit 6. So I'm pausing because I'm thinking about why this was domain. Explicit 1 through 5 were boundary, geometric entity level, selection, recall, and then explicit 6 was domain. But the output entities was adjacent boundaries, exterior boundaries. Okay, so I'm guessing that when we choose a geometric entity level that is different than that of the selection we choose for that coupling, it's referencing, it has to have something at that level to choose. So it's selecting the output entities. So if the domain is the entire thickness of the housing, then the general extrusion is going to be the non-local coupling for the solution of the exterior boundaries of that domain. So the outside, if we zoom in here a little bit and rotate this, you can see this is the boundary of the outside, and this is the boundary of the outside, but then this is also an exterior boundary, but it's now, on the other side. So both sides of this flat, for example, the inside, the edge, and the outside, but not the interior part of that domain, only the exterior boundaries. So that explains why we chose adjacent boundaries, exterior boundaries, because that is where the sound would emanate from, right? Or that's where vibration would come into contact with air and thus propagate as sound or acoustic vibration. Okay. All right, I'm back. This is such a long tutorial. I've had to break it up into 2 parts, and so I'm going to start back up at add material, which I actually already did. I just chose structural steel from the built-in library, and now we're going to move on to the physics. So for all right, starting with multibody dynamics, define the gears mounted on the countershaft. Helical gear, 4th countershaft. All right, So we're going to go under Component 1 in the Model Builder window, right-click on MBD and choose Gears. Right-clicking Gears is up here, and then we're going to choose Helical Gear. Alright, in the settings, and then select Domain 9 only. So we're looking for Gear 4 and the counter shaft, which is right here, but it happens to be hidden, so it's kind of hard to get to. Alright, so when one domain is obstructed by another domain, like in this case I can't get to counter shaft 4 without highlighting domain 4. So what I want to do is go to this little eyeball with the line through it, click and hide, and then I can, if you see here, I'm in the select domains item. So it's the barrel icon. If you do expand this dialog box, you can select boundaries, select objects, select domains, edges, points. I do want to select domains, so as selected, we're going to hide domain 4. And then instead of view all, I want to view unhidden only. And that way, when I'm selecting my helical gear, I can access domain 9, which should be, let's see, where's domain 9? That's gear 17. Okay, so the first one here is domain 9. So that is our 4th countershaft gear. And we're going to label this helical gear 4th countershaft in the label field. Locate the gear properties, and in the end text field, type N4I. So this is going to reference the parameter, number of gears in the 4th countershaft, and in the DP text field, type D4I. So this is the pitch diameter for the 4th countershaft gear. Alpha is going to be parameter alpha, beta is going to be parameter beta. And if you need some reference material if you need to know what those parameters are, you can research gear theory or just Google COMSOL gear modeling. There's plenty of literature and documentation available. So for instance, beta, this is what beta is. If you look at here we go. So this is a good article I found in my research outside of this tutorial, just because I, as a chemical engineer, haven't had a lot of experience with gears. So this really did a good job explaining alpha and beta in particular. So the pressure angle of a gear is the alpha parameter, and I like this little figure. He shows little stick figures jumping off the helical gear, and as noted in image figure 1, the pressure angle is the jump off angle of the characters. So in this direction, whatever angle that is alpha. And here's another depiction of alpha. In figure 2, the line labeled 1 is normal to the tooth profile. So here's line 1. And the line labeled 2 is the tangent to the reference circle. Here's 2. Line labeled 3 is tangent to the profile. And line labeled 4 is the radial line. In this image, the normal pressure angle is labeled alpha. In modern times, it was recognized by AGMA that a 20-degree pressure angle was more suited for most applications and has been used. This value is the preferred value for normal pressure angle. beginning in the early 80s. Another site I found, this is from Engineer's Edge, that had different design equations and depictions of gear variables and parameters you'll need. Like for the pinion and gear, you'll have pitch diameter for both of those. You don't need all of these for COMSOL, but you will need some of them. The center distance, let's see, where's C? Center distance is the distance from the center of the pinion to the center of the gear. That's our pressure angle alpha, helix angle beta. And then in the gear axis section, we're going to specify the EG vector as 1 in the X direction and 0 in the Y and Z. So we can see with our orthogonal label at the bottom, if you don't have this, you can turn it on in the graphics window with your label show axis orientation. It's this little orthogonal icon. So you see red is the x-axis, and that is the direction of the shaft and counter shaft. So that's why we've got a unit vector for the x direction and 0 for the y and z, since the gear axis is in the direction of x. Helical gear is counter shaft. You can create the remaining helical gears mounted on the counter shaft by duplicating the 4th countershaft gear that we just created and resetting the information given in the table below. So let's do that quickly. I'll just fast forward through this part. Alright, so that was all 4 of the countershaft gears. Now we're ready to define the rigid domain, which is the countershaft in the center here. So we're going to go to Physics toolbar, click Domains, and choose Rigid Domain. And then we're going to select Domain 8, which is the countershaft at the center here. And now create a fixed joint. In the Physics toolbar, click Global. Global is here. And choose Fixed Joint. In the Settings window for Fixed Joint, locate Attachment Selection section. And from the source list, choose Rigid Domain Countershaft. So this selects the region or the domain that we just defined as rigid. And for the destination, we're going to choose the helical gear 4th countershaft. We're joining a helical gear to a rigid body. Let's see. You can define a domain as elastic or rigid and join it to a gear or any other. And you can create the remaining fixed joints by duplicating fixed joint 1 and resetting the information in the given table. So we're going to just do the same thing, create pairs, or sorry, not pairs, but joints between each of the countershaft gears and the rigid body, which is the countershaft itself. So we'll just duplicate fixed joint 1 and change the destination. Now define the gears mounted on the main shaft. In the Model Builder window, right-click Helical Gear 4th countershaft and choose Duplicate. So now we're just doing the same thing, but we are doing it for the main shaft now. So we're going to select Domain 10 only, so that's the corresponding gear to the countershaft 4th gear. And for number of teeth in the end text field, type N40. For D, we're just changing it to D40. Alpha is the same. Beta changes to negative beta. And once again, we're just going to duplicate for each of the gears. And then we're gonna do the same thing with the rigid domain. Go to physics, select rigid domain, and label this one rigid domain main input shaft, and select domain 1 only. Here's domain 1. And now we're going to select the rigid domain for the main output shaft. So we're going to right click the main input shaft, duplicate, change this to main output, and select domain 2. Now we're ready for the fixed joints on the main shaft. Fixed joint 6. In the model builder window, under component 1, right click fixed joint 5 and duplicate. And in the settings window for fixed joint, locate the attachment selection section. So we're going to change the source from rigid domain 1 to rigid domain main input shaft, and then the destination is going to be helical gear 4th main shaft. So you can see that these two are the only ones connected on the input side. All this other information is going to stay the same. And then we're going to create a hinge joint next. So going to physics toolbar, global drop down menu, and choosing hinge joint. And in the settings window, we're going to create an attachment from source main output shaft. So the other side of that main shaft. And then the destination is going to be, and the destination is helical gear 1st main shaft. Prescribed motion. In the physics toolbar, click attributes and choose prescribed motion. In the settings window for prescribed motion, locate prescribed rotation motion. And from the activation condition list, choose conditionally active instead of always active. And in the I sub theta p text field, type in factorial equals 1. So this is our deactivation indicator expression. And we're going to create remaining hinge joints by duplicating hinge joint 1 and resetting the information given in the table below. Okay, so careful on this one. We've got hinge joint 4 corresponding to the 5th gear and hinge joint 5 corresponding to basically connecting the input shaft to the output shaft. Alright, for hinge joint 5, another option appears in the model builder window called center of joint boundary 1. So it wants us to select something And you'll notice this property did not appear for the other hinge joints because hinge joint 5 is connecting two rigid bodies. So we need a center of joint boundary. So in the settings window, locate the center of joint section, and from the entity level list, choose point. Changing this from boundary to points. And then we're going to go to center of joint point 1, and this is already cleared, so we want to go to paste so we can type in the selection 151 to 152. And if you want to zoom in, you can do zoom to selection, which is right next to zoom extents, and see the 2 points selected are here and here. You can do control while scrolling out with the wheel on your mouse if you want a little more context on where those points are. You can rotate it. After defining all the gears, now define the gear connections. So you can see these 2 points are the vertical center of the gear, or the center of the end of this output shaft. So this is the Z direction, the X-axis is the gear axis, and you can see the blue dots. This one is the top and this one is the bottom, representing the center of joint points. Okay, so now we're ready to select the gear pairs. And we're gonna go to Physics Toolbar, Boundaries, Global, and choose Gear Pair. You can also do this by just right-clicking on Multibody Dynamics, going to Gear, so you can also get to gear pairing by just right-clicking on MBD, Multibody Dynamics, and selecting gear pairs and choosing from the selection gear pair, worm and wheel, or rack and pinion. Okay, so here's our gear pair, and we're gonna relabel this gear pair 4th. Locate the gear selection section, and from the wheel list, choose helical gear 4th main shaft. So you can see it highlighted in yellow. Pinion list selection, we're going to choose helical gear counter shaft. Locate the gear pair properties. Select the include gear elasticity checkbox. And now we're going to add that gear elasticity. In the model builder window, click gear elasticity 1. And in the settings, locate mesh stiffness. In the K sub TWH text field, type KT. We're going to overrate this with KT, our parameter KT. And for K sub TPN, which is the pinion to stiffness as a function of mesh cycle, we're going to also sub in parameter KT. From the contact ratio and mesh cycle list, choose varying instead of constant. And in the psi text field, type 0.8. So this is our next tooth engagement position in the mesh cycle. Now we're going to create the remaining gear pairs by duplicating gear pair 4th and resetting the information in the table below. In the physics toolbar, click boundaries and choose attachment. In the settings window for attachment, we're going to label this attachment bearing 1, counter shaft. And then for the boundary selection, we're going to choose Explicit 1. Alright, and for the remaining attachments, we're going to just duplicate attachment bearing 1 and reset the information given in the table below. Ready for Hinge Joint 6. In the Physics toolbar, click Global and choose Hinge Joint. In the Settings window for Hinge Joint, locate Attachment Selection section right here, and from the source we're going to choose Attachment bearing 1 countershaft, and destination is going to be Rigid Domain countershaft. So we're creating a hinge joint attachment between bearing 1, highlighted in yellow in the graphics window, and rigid domain 1, which is the countershaft, highlighted. You can create the remaining hinge joints by duplicating hinge joint 6 and resetting information given in the table below. Okay, in the Model Builder window, click Hinge Joint 7. And we're going to add a prescribed motion. In the Physics toolbar, click Attributes and choose Prescribed Motion. In the Settings window for Prescribed Motion, locate Prescribed Rotational Motion section. And we're going to choose Angular Velocity from the Prescribed Motion Through selection. So we're changing this from rotation to angular velocity. And then in the omega sub p text field, we're going to write expression omega times step 1 parentheses t dimensions 1 over seconds and per seconds in parentheses. Okay, and then we're going to go to Hinge Joint 9. In the Model Builder window under Component 1, click Hinge Joint 9. And then we're going to go to Attributes from the Physics toolbar and choose Applied Force and Moment. In the Settings window for Applied Force and Moment, locate Applied On section. From the list, choose Joints. And then locate the Applied Force and Moment section. And in the M, Applied Moment, we're going to write expression negative T underscore exterior ext times step 1 parentheses T in units of inverse seconds. And again, it's saying unexpected unit of input. So hopefully that clears up once we run it. Moving on to Fixed Constraint 1. In the Physics toolbar, click Boundaries and choose Fixed Constraint. In the Settings window for Fixed Constraint, locate the Boundary selection, and we're going to choose Explicit 5. So this is all the nuts and bolts, it looks like, on the housing, or the location where the housing is fixed. And let's see. Okay, that's it. Now we're ready to go to study. So the moment of truth. So let's click on study 1, and in the settings window for study, type study multibody analysis. And then clear generate default plots from study settings. Okay, step 1, time dependent. In the settings, locate study settings section. And in the output times field, we're going to change this from range 0 to 1. I'm going to go 0 to t in increments of t over 2000. So a convenient way to convenient way to dictate how many increments you have. Just your end output, the end of your range over however many increments you want. And then in the study toolbar, click solver, show default solver, the 5 flags icon, 4 flags. And in the model builder window, expand the Sol 1 node and click time dependent solver 1. It'll take a second for that to appear. Alright, so I'm going to let this compute for a while and then I'll be back. The computation took a bit longer than I thought it was going to take. 3 hours, 18 minutes, 19 seconds. So I'm going to keep pushing through this. It's like 10:30 right now, so I'm going to turn my camera off and just see how far we can get. I probably won't finish it, but we'll do some of the results for multi-body analysis. So in the model builder window, expand results and data sets. Right click, study multi-body analysis solution 1, and choose duplicate. In the results toolbar, click attributes and choose selection. So I'm going to go to results, attributes, selection. And in geometric entity selection, we're going to choose changing from entire geometry to domain. I'm going to click on the paste icon, the little clipboard, and enter domains 1 through 2 and 8 through 18. Alright, so it looks like that was all of our moving parts and the rigid body. So gears 1 through 5 on both the main shaft and the counter shaft. And we've got our rigid domain main shaft input, rigid domain main shaft output, and then the counter shaft. Okay, and then study multibody analysis solution 1, 3 Sol 1. So that's going to be our next one. We're duplicating 2, right click, duplicate. In the model builder window, expand the study multibody analysis 1, part 3, and click selection. And we're going to locate the geometric entity level, clear selection, go to our paste icon and enter domains 3 and 5 through 7. So basically anything we didn't select for the moving parts. All the fixed parts, the housing and just the housing. Follow the instructions below to plot the stress and normal acceleration in the housing as shown in figure 4 and figure 5 respectively. So we're going to start with velocity stress plot, surface plot. In the results toolbar, click 3D plot group. 3D plot group is the cube icon. We're going to label this velocity stress. Right click velocity stress and choose surface. So once you click off of it, it changes the name in your model builder window, and now we can right click and we're going to add a surface plot. In the settings window for surface, locate the data section, and for data set, we're going to choose Multibody Analysis Solution 2, or Solution 1, the second iteration of that. Then in our expression text field, we're going to change expression from nbd.disp to velocity.vel. Alright, and then locate coloring and style section, and we're going to choose Aurora Australis. Aurora Australis, I haven't used that one before. Alright, now to add a deformation surface plot. Right click surface 1 and choose deformation. Or sorry, we're adding an element to the velocity surface plot. And locate the scale section. Select the scale factor, and we're going to change this from about 1/4 to 1. Surface 2. Model Builder window, under Results, Velocity Stress, right click Surface 1 and choose Duplicate. So to the same node, Velocity Stress, we're just adding a second surface plot. Oh, right click Velocity Stress, Surface. Oh, well, that's not. Let's do it the way they told us to do it. Because if you create a new one, then you have to do more work. So let's just duplicate the one we had, and then there's slightly less work. Duplicate. In the settings window for surface, locate data section, and then we're going to choose Multibody Analysis Solution 1, 3 in parentheses. So the third copy of that data set we made is our source data. And then in the expression, we're going to change this from velocity to mesis. So it's going to be the von Mises stress. Locate coloring and style, and we're going to change this to traffic light. Oh wait, that was thermal light. Traffic light. Okay, and then for our range, I'm going to change this to manual range. I'm going to expand it. Click manual color range. For the minimum, we're going to override this and put a minimum of 0 and a maximum of 2E7. So that changes our color scale gradient to something slightly more useful. Not slightly, significantly more useful. Okay, velocity stress. So now before we go any further, we've already got our velocity magnitude on the moving parts in this blue to white color gradient. And then on the housing, we have our von Mises stress in newtons per meter squared, which is a force per area. That's a pressure in the red to green. So as you can see, as you might have anticipated, just by physical intuition of the problem, we have a higher stress around those bearings where the moving parts meet the housing, the fixed parts. So where vibration is emanating out of the gear components, we have a red zone, so a very high von Mises stress, relatively high. And then the green is the low, going down to 0. And you can see around the screws of the housing, it's slightly higher with this yellowish green color. And then of course with the velocity magnitude, you can see that the outer components of the gears, let's zoom in a little bit. You've got sort of this light blue at the central axis, which makes sense because you have lower acceleration about the axis, or on the axis it would be very near 0. And further away, you've got to accelerate faster to rotate at the same speed. So it's going to be the highest at this blue value of 5 meters per second. Okay, so let's continue. Velocity stress. In the Model Builder window, click Velocity Stress, and in the Settings window for 3D Block Group, locate the color legend. Velocity stress, color legend. And then position list. From the position list, choose right double. Oh, I don't have the right thing highlighted. There we go. So, position right, we're going to change to right double. So instead of overlapping onto the useful part of our graph, now they are doubled up on the right. So just another way you can customize your legends. And in the velocity stress toolbar, click plot, which we'd already done, so that's complete. And then velocity normal acceleration, we're going to right click velocity stress, click duplicate. I'm moving kind of quickly here just because I go into detail in a lot of other tutorials and take my time on how to create surface plots. So this is how to do these is less interesting than actually looking at the results and interpreting them. And I've spent a lot of time on the geometry part of it, and the helical joints, or the helical gears and joints for those, because that is new and that is a little more complex for this tutorial. Alright, so zooming through these plots, we're going to label this new one velocity dash normal acceleration. Okay, and then we're going to expand this velocity normal acceleration, go to surface 2, and in the settings window for surface, locate the expression section. So where it says NBD.mesis for multibody dynamics when mesis stress, we're going to type AN, which is the expression we defined in our variables. It was like 3 days ago for me now, so it's been a while, but I vaguely remember defining that function, or that variable rather. And then we're going to go to the range, and as you can see, the units automatically change, detecting the correct units for that expression. And we're going to change the range to manual color range, or no, we're clearing manual color range, so it goes back to default. And then for the color style, we're going to choose rainbow. In the velocity normal acceleration toolbar, click plot. So as you'll notice, for this second velocity grouping we've created, we've got the same surface plot for the velocity, but now our housing is showing normal acceleration rather than when mesis stress. So you can see normal acceleration versus the velocity magnitude of the gear components. And what do we see here? Okay, so now we have sort of an inverse gradient going on here with normal acceleration, where you have purple around the counter shaft, so a value of about -4 times 10 to the third meters per second squared. Where around the main shaft input, we've got a high value. You can see some slightly red, orange here. It's about the same magnitude, but positive value. And if we go to the other end, I'm sure we'll see the opposite of that. So again, here on the counter shaft, you see the high end now, and around the main shaft output, the roughly the same magnitude, but opposite in sign. Follow the instructions below to plot the time history and frequency spectrum of normal acceleration as shown in figures 6 and 7 respectively. In the home toolbar, click Add Plot Group. I'm going to label this 1D plot group as normal acceleration. You guys, this is going to be like a 3-hour tutorial. I think I'm on page 29, and this is a 48-page tutorial. Oh my gosh. We got real programming to do here and methods. Okay, that's alright. I'll take a week to film it. Okay, so where was I? We were on page 27. Okay, point graph 1. Right-click normal acceleration and choose point graph. In the settings window for point graph, locate the selection section, and we're going to go to paste selection and type 879. Very convenient that we're doing a tutorial, and hence we are given the points of interest. Alright, so that's our point, and click OK. In the settings window for point graph, locate the y-axis data section, and in the expression text field, type AN. Again, we're replacing MPD displacement with our normal acceleration variable. Locate the x-axis data section. From parameter list, choose expression. So just below y-axis data, we have x-axis data, and in the expression, I'm going to go to parameter expression and replace with AN. Oh, sorry, not AN. We're going to replace with MBD Multibody Dynamics .hgj 7.th. From the unit list, choose degrees. So default is radians, we want it in degrees. Select the description checkbox. And in the associated text field, type main shaft rotation. Rotation. Here we go. And click plot. Alright, so there you have it, normal acceleration in meters per second squared versus main shaft rotation in degrees at our given point 879, which is on top of the housing and roughly in the center. So the way the housing accelerates normal to the gear axis is, I guess this makes sense if you, so now we're going to do point graph 1. In the model builder window, expand normal acceleration frequency node, then click point graph 1. Oh, I missed something here. In the model builder window, right click normal acceleration and choose duplicate. And then label that normal acceleration. Right, and then we're going to expand this and click on point graph 1 node, locate the x-axis data section. In the parameter list, choose discrete Fourier transform. From the show list, choose frequency spectrum. In the normal acceleration frequency toolbar, click plot. And there you have it, Fourier coefficient versus frequency